Cool. All right, so we just finished unit circles. So now that we know unit circles, we're going to see how that helps us out with solving right triangles. Usually, in order to really take advantage of the unit circles, our right triangles are mainly going to be the 30, 60, 90 triangle. So well, let me click in here and then I'll start writing on the screen. Of course, it signed me out. All right, perfect. Give me a second. All right. So we are doing pre-calculus. We just finished our unit circle, like I said, and we're gonna do problems with right triangles. So you guys have probably done this before. The main idea with trig, now that we're doing pre-calculus, is really mastering how to use the trig functions and understanding how you can use this angle to solve for your ratios. So your basic trig ratios are your opposite over your adjacent, which is tangent, your adjacent over your hypotenuse, which is cosine, or your opposite over your hypotenuse, which is that. So basically, think about it as the sine, you take an angle, you spit out, you take a theta, you spit out a fraction, some kind of fraction, some kind of decimal, and that fraction will help us determine these sides. So if we know one of the sides, it helps us solve for the rest. So our goal for this unit is going to be using that information. So we're going to do in this lesson, you will find unknown measurements in right triangles. And the reason why it's important is right triangles, it works perfectly because if it's right, we know exactly the height of it. If it's a little off, we kind of have to make up that gap. And we'll do problems later on how to make up that gap. You guys probably did it in geometry before, the law of sines, law of cosines. But let's get into this one. So they give an example with an uh, oil platform, the radar, and they're going to talk about how they use radar in degrees to determine distance. So let's get into the actual problem. So we already know how to solve for a side. We just use the Pythagorean theorem. When we're using this, we're going to be using our trig functions. Some of the angles. So, and we can also find the rest of the angles just by knowing that every triangle has 180 degrees. So if we know this angle, we know this angle. Mainly because we're only going to be dealing with right triangles. So these two angles have to equal 90 degrees because 90 degrees of that 180 is being taken up here. So right off the bat, if our triangle has 180, one of the angles is 90, the remaining angles have to also be 90. All right, and our next thing here is these ratios will never change. So the reason why they won't change, even if your triangle is different, is let's say we're talking about this line. Well, what happened here is we made this shorter and we made this shorter. Also, if we go further back, the line's getting even taller. So that's how come these always work. So I think it was Nick. Oh, look, and Nick's here. He knew I was going to talk about him, so he decided to show up. So I think it was Nick that said, like, why do we have to use the unit circle? Well, if we pretend that our radius is always 1, we can, by extension, just kind of increase the size of the circle. We can just multiply everything because the trig ratios are always the same. So for example, if this is like, let's pretend from here to here is 2, from here to here is 3, and then now we talk about this longer side, and this orange side, let's pretend this is 4. Then this orange side over here is going to be 6. The reason being is we doubled this, so this doubles. So if this is like 1, over here, this is going to be 2 because everything is doubling. So that's why we learned the unit circle, because we know how to deal with this is 1. If we make our hypotenuse bigger, we just have to multiply it by whatever that side is. That's what it means here by our ratios are always the same. And for that example, if I do A to B, where's A to B? So if A to B is this 4, and then this is 2, that means my ratio is 4 divided by 2, which is going to be equal to, if this big thing is 6 and this little one is 3, it makes sense that 6 divided by 3 is equal. So that's what it means by our ratios are always the same. We're just making it bigger or smaller, and the fractions stay the same. So, they're literally explaining what I just said. The unit circle, we can just make it bigger. So by knowing the unit circle, we're already at an advantage. We're just going to have to multiply it. So they're literally just saying what I just said. One of the few times I agree with Inventum. All right, so here's our triangle. So we already know this. It's already on that sheet of paper that I gave you. Or you can always go to Google Classroom to grab it. So let's say that sine is always y. That's always that. The only difference is, let's say we increase it. We're just going to multiply it. So right here, they're just putting in our definitions, which is obvious. Secant, and these are ones we haven't talked about yet. Cosine is the, how can I describe this? It's the reciprocal of sine. So cosecant is just our sine flipped upside down. Secant is the opposite, not the inverse. I keep wanting to say inverse. It's the reciprocal, meaning we flip it over. I don't know how to spell reciprocal. Reciprocal. You really know how to spell this. I'm sorry, guys. So it's a reciprocal of this cosine. So if we flip cosine over, so in other words, if I say secant theta, I can literally just substitute it in with cos 1 over cosine theta. It's the same thing. And cotangent is obviously tangent upside down. All right, so this is where we get SOHCAHTOA from. Oh wow, somebody actually drew someone soaking a toe. Soak a toa. Huh. Some people that hear this like always say suck a toe, and I'm like, no, it's SOHCAHTOA. And someone literally went here, soak a toe. Well, you guys already know this sine, cosine, so that's an easy way to remember it. I think I kind of went over this when we went over the unit circle stuff, so they're just connecting the dots with it. So right now, we're going to do this activity. It's like find the 6 trig functions. I always hate when they make us do all 6 because I'm like, the rest don't even make sense. But let's go into our equation editor. So our 6 trig functions are sine, theta. Our theta, they labeled it as this sign right here. So remember, our angles, our sides are always, what's the word? They're always respective, relative. I have to remember, I'm like, one guy, Einstein, he talked about it. It's relative to whatever we're talking about. So if we're talking about this, it's going to be a different opposite than if we're talking about this one. So sine theta, our other one would be cosine theta, and we have tangent theta and tab. Oh, does tab not work? Tab does not work on here. The inverse of this would be cosecant. The way I always remember it is you would think that the cos would be the same, but it's kind of the opposite of that. Probably a really bad way to remember it, but it helps me. So the reciprocal of cosine is secant because it doesn't have the co. The reciprocal of cotangent, or the reciprocate of tangent is cotangent. Where's my, there it is. All right, so if we're doing this, sine. Sine is opposite over hypotenuse. And if you guys ever have to write it down, when I took trig, I literally just, the first thing I would do would write SOHCAHTOA on my paper. So you guys can have this on a post-it note or something. So we're going to do opposite of theta, which is 12. So remember, we're going to hit this little fraction button. I'm only going to do the first one like this so you guys can remember how to do it if you guys forgot. 12, our hypotenuse is still 13, so we're going to do 13. And then for the rest of them, so adjacent of this is 5. So I'm going to do 5 over 13. And then I'm going to do my opposite over my adjacent, which is 12 over 5. So if I wanted to do the opposites of these, it'd be 13 over 12. It would be 13 over 5, and it would be 5 over 12. So I'm not the biggest fan of when they ask you to do all 6, because my thing is, if you know how to do 3 of them, you know how to do the other 3. You just flip them over. Obviously, your guys' answer doesn't have to do this. You can put it in there if you want, but that just helps me. All right, and the next one. So now they want us to do it again, but now our theta's up there. So if we do our sine theta, our opposite is 4 over 7.5. Our cosine theta is our adjacent this. So one easy way that I've seen other people do it is they identify it. So they identify if this is our theta, this is A, our opposite would be here, and our hypotenuse would be here. It makes it easier when you're thinking SOHCAHTOA. So this, ooh, I put 7.5. I meant to put 8.5. Sorry. Hypotenuse. And the other one is 7.5 over 8.5. Our tangent, this one is opposite over adjacent. So this is 4 over 7.5. And then you can do your other trig functions. You don't really need to a reminder for that. Just remember sine, cosecant. 8.5 over 5, or 4. Cosine is secant. 8.5 over 7.5. And tangent, or cotangent. Cotangent is 7.5 over 4. And the rest, well, might as well do them. I was like, you guys can do the rest, but might as well do them together. That way you guys can take notes or screenshot, whatever you guys need. So if we're doing this, opposite, because our angle here, we're going to go opposite to it. Adjacent is this, and our hypotenuse is this. So when we're doing this, sine theta equals opposite 5 over hypotenuse 10. And our next one would be cosine theta equals, what is it? Adjacent 5/3 over 10. And then tangent theta is opposite, so 5 over 5 and third. Sometimes Admentum gets picky and it's like, hey, if you do this, you would end up getting 1 and square root of 3. So you would have to get rid of this by multiplying the top and bottom by square root of 3. And that'll give you square root of 3 over 3. It's picky like that, but then again, I didn't even reduce this to 1/2. So you guys can either leave it like this, or if you want to do it the way with no radical at the bottom, that's fine. So sine flipped over is cosecant, which would be 2 basically because it's 10 over 5. Cosine flipped over and reciprocated. Secant theta is 10 over 5 square root 3. And last one, cotangent theta, that's going to be 5 square root of 3 over 5. Is this making sense so far, guys? I'm sure you guys have done this before, but is this at least a good refresher for you? Yeah. You're like, I forgot all of this, and I'm just remembering it right now. Well, at least you're remembering it now? Maybe? All right. So then again, here it's showing you how to do it. So we're going to use these components to solve it. I don't know, I don't know if this unit's going to cover inverse trig functions. Inverse trig functions are really useful for figuring out other things. It doesn't look like it. It looks like it just wants us. So these are our case scenarios. So solving a triangle, solving the triangle when given an angle at one side. So they want us to solve a missing side of a triangle. So the way we do this is we're going to use our angle, whatever trig function. So you have to identify your trig function first. So if they want us to solve for our C, we have to identify that our C is our hypotenuse. And if we're using angle alpha, they only gave us angle alpha. And they gave us sine B. Well, according to this, if this is the angle given, we know our adjacent. So this is our adjacent, this is our opposite, and this is our hypotenuse. So when we're doing this, what we're trying to do is, sorry guys, we're doing cosine, we know our theta, we know our adjacent, but we don't know our hypotenuse. So that's all we're doing here. We need to identify which trig function. We're not going to use sine because we have no idea what our opposite is. So that's the biggest part, is just identifying when you need this. Sometimes you're going to have to solve for sides using the Pythagorean theorem. Sometimes you might solve for angles, just subtracting the angles. But otherwise, that's usually how we would do this, is just identifying our trig function. So here, if I'm doing this one, my theta is 50. I don't care about my alpha right now. They want us to solve for the hypotenuse. They want us to solve for C. I only know my A, which just so happens to be next to the angle, so it's my adjacent. So I need something that involves my A and my H. That's C. So I have to do cosine of 50 equals 8 divided by H. You can call it C if you want, it doesn't matter. So what I do here is I need to get my H to the other side. So I'm going to multiply both sides by H. And then I need to get this to the other side. So I do H is equal to 8 divided by cosine of 50. One thing that you can notice here is if your H is at the bottom, you can just swap this and this together. It's done by cross multiplying technically. Cross multiplying and then dividing. This step, if we cross multiplied, it would be 8 times this times that. And you can just divide. So if your h is on the bottom, just switch the cosines over. If your h is on the top, you're just going to be multiplying. So 8 over cosine of 50. So we're going to use our handy little Google calculator. You guys aren't doing inverses, but it's a good refresher. So let me go to calculator. Here, so we're going to do 8 divided by cosine of, what's our problem? 50. So you need to have a calculator for this. So I recommend the Google calculator. It's been working good so far. Let's see if it lets me down right now. It might have just let me down right now. Oh, make sure it is set to degrees. I had it set to radians. So that wasn't the Google calculator's fault. That was my fault. I can't get mad at Google. We're using Google Hangouts right now. I'm bad about Google. They do eat all your RAM. All right. So I did have it on degrees this time, and it gave me the answer as 12.44. So the closest answer would be 12.4. Why are you trying to like play Fortnite while sharing your screen or something, Nick? That's why it eats all your RAM? No? All right. So the next thing is solving an angle. So the next thing is solving an angle. So, okay, so we are going to use the inverse function. So remember how I said I wasn't sure if we were going to cover this or not, but it looks like we are. So what we're going to do here is a normal trig function takes an angle and spits out a fraction, but an inverse trig function takes a fraction or a decimal, however it is, and it's going to spit out an angle. So that's what it's telling us here. This is how we're going to be able to solve for an angle. So the first case we're solving for a side. This next one, we're going to solve for an angle. And if we need to solve it for a side, we just have to use the Pythagorean theorem. So I don't know why it didn't tell us the third case. I guess because they're like, oh, you can use the Pythagorean theorem, it's fine. So if we were to solve this, we want to solve for angle beta. So first we have to identify our angle. They want us to use this angle, angle beta. Usually I call this big B because it's opposite of the little b, but they're calling it this. And then I would call this big A because it's opposite of little a, but they're using alpha and beta. So I know my opposite angle and I know my adjacent angle. So that means opposite and adjacent, this has to be tangent. So we're going to do tangent beta equals 6 over 15. But in order to get rid of this, what we're going to do here is we're going to have to find the inverse. So in other words, the b is equal to the inverse of 6 over 15. I know I could have done it the other way around, but I wanted you guys to see the relationship here between these two. So the inverse is not the same thing. So tangent inverse is not the same thing as cotangent. I just wanted to make that clear. Tangent inverse would have been like, tangent inverse takes a fraction, spits out an angle. Cotangent still takes an angle, but it spits out the opposite thing. It spits it out flipped over. So Cotangent and all those are the reciprocal functions. They're not inverses. I know it's confusing, and honestly, I hardly use reciprocal functions. They're used way later on, but for the most part, you can always just substitute with the reciprocal of one of the three functions. So here, I'm just going to plug this into my calculator. So I'm going to go to Google. Google, you don't have inverse functions? There's got to be more info. No, Google, why? All right, so apparently Google has finally let me down. I don't have an inverse function button. So, let me see if I can find another scientific calculator. Scientific calculator. I want to find a free one. That way, in case you guys don't have. All right, well, Desmos, let's see how good your scientific calculator is. I haven't been a fan of this calculator before, but we'll see what we can do here. And I don't see an inverse function. Oh, there it is. So if anything, guys, use desmos.com/scientific just for the inverse function. I'll look to see if I can find a Google calculator for it. So I need to find the inverse function of 6 divided by 15. So I'm going to do tangent. It already puts the parentheses for me. I'm going to go to main. And then I'm going to do 6 divided by 15. And it already treats it like a fraction. Because dividing and fraction, same thing. I'm going to close my parentheses. Nope. Close my parentheses. Hit enter. And according to this, it's 21.8. Let's see if that's... Oh, this is not Desmos' fault. I forgot to switch it to degrees. Oh, never mind. It was on degrees. Desmos, we have a problem here. Why isn't this working? Opposite. Why did I call this adjacent? This is totally the hypotenuse. I mean, how come nobody corrected me? Nick, are you asleep again? Well, at least you're honest. My bad, everybody watching at home. Garrett's probably going to be like, bro, I was sleeping through class and then watch your video and then you make a big mistake. So we're doing sine inverse. I'm so sorry. Sine inverse of 6 over 15. So, well, still can't get mad at Desmos, I guess. I mean, I can. It's just not going to be productive. All right. So let's see how we're doing. All right, 23.57. I think I saw that one. Yep, 23.6. So make sure you identify your sides correctly. That was part of the lesson, guys. I was teaching you why it's important to identify your sides correctly. This isn't adjacent, but more importantly, it's hypotenuse. So I get that question a lot. It's like, well, isn't this an adjacent side also? Yes, but it should be treated as hypotenuse first. I just made that mistake. Don't make that mistake. It gives you the wrong answer. All right. So let's go to the next one. So now we're going to talk about using this in real life situations. We can use trig functions in real life by all right. So in this case, if you're looking at an object, in this case like a plane, we can figure out how the angle of elevation. So let's say we want to figure out how far this object is. We would need to know the hypotenuse. What? Well, what if you're playing Call of Duty and you need to shoot this down with a rocket launcher? Another way of using trig is when we're using the cardinal directions. So when we're talking about how many degrees away from north. So let's say we're traveling so far, it's a zombie apocalypse, and it's like, all right, I know that safety is over here, like 30 degrees away from north. So we're going to need this angle, but I can't go directly to it. How far north do I have to go? And then how far east do I have to go to get to that spot? So that's another way you can use trig in the real world is triangles. Triangles, trig is big on triangles. This is trig. This is trig, not algebra. All right. So next thing we're gonna do is we want to figure out how tall this building is. Well, we're not gonna measure how tall the building is, right? Like that's kind of hard. So you might have seen people when they do construction. Oh, actually, Nick, did you guys have like a construction class where you had to measure an angle? Use your fingers to measure angles? Well, let's say you're on. What, do you have a measuring tape that can measure this entire building? You really don't want to do trig when you're working, do you? So, there's a tool that surveyors use to kind of measure angles of elevation. So, they're like, all right, I'm this far away from the building. The angle is this many degrees. So, I can figure out what the opposite is by knowing what my adjacent is. This one is opposite and adjacent. I did the right sides this time. So that's why they're plugging it in here. We're 60 feet away. We can take the tangent of this, multiply it by 60, so these cancel out. And we figure out that this building is 221 feet tall. Or it's a monument, sorry. That monument is 220 feet tall. I don't think your measuring tape is 221 feet, Nick. A phone measuring tape. Okay. But how do you think those phones figure out the height of buildings? How do you think those apps figure out the height of buildings? They're using trig. That's what the programmers did. The programmers used trig to have your little cell phone figure out how far that is and then figure out how far this is. And then it's like, oh, okay, cool. This is how tall the building is. They're using trig. So they figured out a way to program the phones to do trig just by looking at it. So, no, they don't do that. The app has a calculator in it that runs all of these trig functions for them. So that's why, like they, no, that would take forever. It's much easier to put a program that knows how to do the trig in it. So let's see if we can figure out how to do this trig too. So I'm assuming they're talking about, okay, so we're trying to, so a builder, so this builder here, this guy doing construction, he wants to figure out how wide the river is. Well, he can't throw his measuring tape across the river to figure out how far it is. That's just not possible. But what he can do is be like, all right, so I'm going to mark right here and I'm going to look straight ahead. Perfect 90-degree angle. And then I'm going to walk a couple of feet and I'm going to measure from here to there about how far this is. So now I have this angle. I don't know what this angle is, and this hypotenuse doesn't even matter. But I do have my adjacent, and I want to figure out my opposite. So by doing that, by figuring out the angle it takes for him to look over here, how far he needs to turn. So if he's looking this way, he needs to measure the angle at which he's looking to get to measure that exact same spot. So you can figure this part out. So what's happening here is we are going to figure out our opposite using our adjacent. So we're using tangent of 43 degrees. We do not know what our opposite is, so we're going to leave that as an O. And we're going to know that our adjacent is this 90 feet. So in order to figure out the opposite is equal to 90 times tangent of 43. Is that making sense? So then we go to our little, no? What does it, oh, okay. You're like, nothing makes sense when you're tired. All right, so I'm gonna do 90 times tangent of 43 degrees. Oops, 43 degrees. I just use my keyboard to type it in. I'm pretty sure I should recognize that that's multiplying. So I enter this in, and I figure it out that it's 83 feet. So 83 feet. The further we walk away and the bigger the angle and the smaller the angle we get, the more accurate this kind of becomes. So that's why you went 90 feet. So this is good. So now we can figure that out. So make sure you're typing in your work here. The next one, a trailblazer hikes up a mountain. According to the pedometer, he traveled 2.7 miles. His altitude is 2,007 feet. What is the angle of elevation of the mountain? So he's traveling up this mountain. He traveled 2.75 miles. Well, we need to convert this to feet first. So we're going to have to take the number of feet in a mile and multiply it. So let me pull out my smaller calculator. 2.75 times 5280. So we're going to get 14,520. So we're going to replace that with the miles. That way we have it all in feet. All right. And now we're going to use opposite over hypotenuse. We're going to use sine of theta is equal to 2100 over 14,520. So remember, in order to get rid of sine, we have to use inverse of sine. Inverse of this fraction. So let's use Desmos because Desmos is the only one with inverse apparently. Make sure I put a fraction. Well, let me type this in. 2100 divided by, oops. 2100 divided by 14,520. My parentheses, and I get 81.57 degrees. So if I look, let me look at the submission. 81.3 degrees. Oh, it is 81.3 degrees. I was looking at this top one first. Yep. So pretty accurate. So far it's not disappointing. Oh, they Edmentum said like that. You don't have to multiply it right away. Just multiply it at the bottom. If you do this though, make sure you have double parentheses when you're entering it into Desmos. The reason being is if you don't, or if you use a different type of calculator, sorry, Desmos will show you that's underneath. But if you're typing it in a regular calculator, it looks like this. Make sure you put parentheses here. The reason being is you want this number to be at the bottom. So you do want to put parentheses so the calculator knows, hey, I want to multiply this before I do division. Otherwise, the calculator can be like, take this, divide it by this, and then multiply it by that, which would be wrong. All right, what time is it? Oh, are we going to be able to finish this unit? We might be able to finish this unit, guys, or this module. Sorry. Speed run. It's what's it called? Blah. I don't know. Nelson says he can speed run Minecraft, but I doubt that's possible. So a surveyor looks at this, and so he's 75 feet from the building. Obviously you can't measure the building. And the angle of elevation is 67.5 degrees. And he wants to figure out how tall is this building. Opposite and adjacent. So we're going to do sine of 67.5 equals our opposite of divided by 75. So when we put this in, our opposite equals 75 times sine. Ooh, that's a terrible looking sine. Sine 67.5. Cool. So let's put this into Desmos. 75 sine. Apparently typing in sine doesn't work. Click it. 67.5. Oh my gosh, I keep hitting the parentheses by accident. 67.5 parentheses. And our answer is 62 or 69.3. 69.3 or 69.29, but I have a feeling it's going to say 0.3. Oh, actually just went straight into feet. Wait, what happened here? What did I do wrong? Oh, wait, hold on. Give me a second. Nick, how come you're not correcting me? No, that's right. Opposite. Oh, it is wrong. You're right. What trig function was I supposed to use, Nick? Not that one. I'm dealing with opposite and adjacent. What trig function is that? What trig function has opposite and adjacent? Yeah, which one has opposite over adjacent? No. This one has opposite over hypotenuse, and this has adjacent over hypotenuse. It has to be tangent, yes. That's the second time I confused my sine with my tangent. I don't know what's up with me today, guys. I'm sorry. How is it so? It's tangent. Are you messing with me? Okay. I was like, what? All right, so let me get rid of this. Put tangent in there. There we go. That's right. So, oh my gosh, I keep messing those two up together, guys. I'm sorry. This will be it because apparently I need to eat. All right, so a traveler across the country spots the arch. She has read that the arch is 330 feet tall. Her angle of elevation is 3%. How far away is she from this? So she's like, hey, I can see the top of that. The top of that is 630 feet. Well, my little measuring thing says that's 3 degrees. How far am I away? So this one is tangent because it's opposite and adjacent. Tangent of 3 degrees equals our opposite, which is 630, over our adjacent, which we have no idea. And oh, they want it near 10th of a mile. They're mean. If you guys leave this in feet, I don't care. So, all right. So what we're gonna do here is we're gonna switch our adjacent and our tangent. So adjacent equals 630 divided by tangent of 3. So what I'm going to do here is I'm going to do 630 divided by tangent of 3 degrees, and I get that many feet. Well, if you guys want to do it in miles, which I believe is 5,208 feet per mile, feet in mile, 80, not 08. We take our answer. I'm going to copy this and divide that by 5,280. And it's about, it wants the nearest tenth, so we look at this 7, so it's 2.3. So this becomes 2.3. I don't know what this little weird symbol is, but 2.3 is our answer. I don't, well, let me see. IO. Are we almost done? I'm almost thinking that we could finish this module. I think we can finish the module. Um, oh my gosh, yes, we can finish this. All right, so this one. Suppose a surveyor stands on this. The roller coaster is that far away. The angle of elevation is this. How's the height of the roller coaster? Mm-hmm. Yep. And you want to know how tall that roller coaster is. Or even if you want to know how your app does it, this is how your app does it. It figures out how far away you are, and then it's like, all right, cool. So then this roller coaster, it's not like perfect. What it's doing is it's kind of like going like, oh, we're probably this far away, and it's probably this much. So this we need to figure out our opposite. So it's using these ratios, this fraction. It's like, okay, it looks like we're about that far away. So the fractions are the same, no matter if you're getting closer or further away. So here we're going to use our tangent ratio because it's opposite and adjacent. So tangent of this equals opposite over our adjacent, which is 60. So what we're going to type into our little decimals calculator here is we're going to 60 times tangent of 80.3. 60 times tangent 80.3. I don't think that's the right tangent. I forget, you have to type it in. And we get, so that roller coaster is pretty tall. It's 351 feet tall. Whoa. Is it? I don't even know. So, since Nick wanted to know about real life situations when you're doing radar, you don't know, are you going to join the Navy? All right, so this helps you find the boats. So if you know the angle and you have an idea of like how far out it is, that's how this ends up working. It helps you figure out the angle. When you are, the radar has detected, oh, so it's going through the scenario. It does the radar, and then it figures out the degrees, and it figures out how far that is. So within this, it figured out how many nautical miles it is using range and bearings. So you can convert this into X and Y axes. And from there, you can use your little triangle. Trig is all about triangles. Use degrees and right triangles. And basically what's happening is it starts figuring out how fast the boat is going by figuring out the distance over and over again. So this is how it can calculate how fast the speed is based on the change in distance. And then from there, guys, as always, watch the video to kind of sum it up. And yeah, we were able to do an entire module in one day. So this weekend, what's up?